intro slides.
Hello, everyone. This week in the Causal Inference seminar, we have Mihaela van der Schaar from Cambridge. She'll talk about the causal discovery letter, unraveling governing equations and beyond using machine learning. So this week we'll have an unconventional format. Mihaela has invited some of her students to join the meeting, and we would like to have a discussion after Mihaela's talk, which will last about 45 minutes. So if anyone from the audience would like to join, please send a message to us through chat. The questions today will be handled by Dominic. Would you like to add anything, Dominic?
So as usual, just please submit your question via Q&A. As said before, we have several of Mihaela's students today, so I think they will be very responsive. So I really encourage you to post all questions. Yeah, and without further ado, Mihaela, please take us away.
Thank you. I would like to ask you to allow me to share screen.
Can you stop?
I think you need to stop. I think you need to stop sharing.
Yeah.
Okay, that's good. Hopefully now it will work. So thank you so much for having us. I didn't realize that the seminar will really have a very international audience. I'm really quite delighted about that. And as Chinuan said, I'm going to talk to you today primarily about my view on causality and why I believe that the discovery is the next frontier in this particular area. But before I do any of this, I'd like you to meet our lab, and I highlighted here students or postdoc that are working on causality. So you see that around half of our lab is involved in some shape or form with causality. So, and we are working on a very broad range of topics. So it's a topic that's very, very dear to our heart. And today I'm going to have with me Zhaoji, Jeroen, Juliana, and Christophe, who are very keen to discuss with you as well. So my plan is to start by talking about the discovery ladder, which I would like to propose as a new frontier and a new way of thinking about the journey we are on in causal discovery. Then I'm going to talk very briefly about more historic work, since our lab is working on causality for roughly 10 years now, first on causal effect inference in the static setting, and then for many years already on the dynamic setting. Then I'm going to stop and ponder why don't we make a bigger real-world impact with causality and introduce this idea of causal deep learning. And only if I have time, I will tell you about clinical trials. So my former colleague at UCLA, Professor Judea Pearl, has introduced his ladder, and I will dare be ambitious and introduce a slightly different ladder. So we know that, of course, we are still very much in the area of machine learning, and I'm a machine learner in the association world, but we are increasingly starting to make progress with causality, and your community, your esteemed community, has made many contributions to it. But what I think that we need to go further is really one step even beyond. And I'm going to advocate that the step beyond is discovering from data governing equations and dynamical systems. Why do we focus on that, and why do we believe for this to be even higher on the ladder? Is because such governing equations, which are compact and closed form equations, provide us for dynamical systems with interventions to provide true understanding. They are concise, they are generalizable, they enable us to think about equilibria, they are transparent, they are interpretable to human experts. And you may wonder at this stage what type of governing equations we have in mind, and you will see some more familiar equations that come from the world of causality a little bit later. But for now, let's just think physics, because most of us have seen these equations for the first time in our physics classes. And you see here examples from physics, but in our own lab, we are even more interested in discovering, using machine learning, governing equations of dynamical systems such as human body or more generally complex systems, whether it is in medicine, physiology, pharmacology. But we believe that this agenda is generally important, whether it's physics or any other area of science. And in particular, I'd like to start by focusing on discovering dynamical systems from data in the form of ordinal differential equations. And they are really at the core of describing dynamical systems and a lot of key problems in medicine. And this is a very hard problem, and one which was not solved for many years. And the reason this is tricky is, so first, we are excited about this topic because, as I mentioned, it can describe continuous time dynamical systems, and they are ubiquitous. And learning this from data is hard, but if we could do it, if you can discover using machine learning from longitudinal data sets such ordinal differential equations, then we really have structural knowledge. And this is very important to create insight and make true discoveries. So what I have in mind here is we have data sets and we would like to discover from it a system of ODEs. And this is a challenging problem that, as I mentioned, has not been solved for many years, is because derivative is not observed. So conventional methods such as symbolic regression are not applicable. And derivatives of it, for instance, two-step symbolic regression, are well known to fail in many settings. And also even opaque. What I'm interested here is discovering transparent ODEs. But even if you think about the world of deep learning, neural ODEs, even neural ODEs which do not fulfill our stringent requirement of transparency are failing often because the true initial condition is unknown and is difficult to infer, and also is computationally challenging. Fortunately for me, I would say very fortunately for me, I have brilliant students. Zhao and Christophe, who are on this call, came up with a brilliant idea to solve and crack this problem. And this is a paper that appeared a few years back at iClear. Let me tell you a few things about it. How they were able to solve this problem is by realizing that we can use the variational formulation of ODEs to attack this problem. And this variational formulation, if you go back into history, it goes all the way to Euler. But some of the insights we use here are slightly more recent. And the idea is that we can characterize ODEs without referring to the derivative. So what we are doing, in effect, we are introducing these functionals which do not involve the derivative of x. What they do involve is the derivative of something we construct, which is the derivative of g. And if we choose g in such a way that the derivative is easy to compute, then also computing the functional is easy. And the variational formulation of the ODEs that the differential equations hold, even only if the functionals are equal to 0, for all the continuously differentiable functions vanishing at endpoints. Now, in the code, we are using this to build our own theory. You see here just a glimpse of it. And rather than make you look for a lot of pages and pages of formalism, which I think is very powerful and beautiful mathematically for the ones among you that are inclined to look at such beautiful work, I'd like to highlight that this is not just what I call decorative math, which many papers unfortunately have. In this paper, we don't have decorative math, we have useful, powerful math, because it helps us derive directly how to think about solving this problem. It provides us a way to discover the basis that we are using in our algorithm. And in particular, one of the many bases that fulfills that is the Fourier sign basis, which for me, as a former signal processing PhD working on wavelets in my thesis many years back, is very satisfying. So what with this? On the basis of this, we are able to estimate trajectories in the first step and all the pre-specified testing function. And what we do is we are able then to use actual symbolic regression. And the reason we are able to do that is because we now no longer need to deal with the derivative of x, but rather to this derivative of g. And g, as I mentioned, is something we construct and is nicely differentiable. So hence, searching in this set of functions is very easy. How well do we do? Well, to evaluate the performance of the code, we evaluated first on a series of synthetic experiments where we have observational data with noise, with errors, with limited observations or irregularly sampled observations. And we try to unravel from this data things we do like we do not know, but in effect, we do know them. And we want to know whether we indeed recover what we do know. And then I'm going to tell you about some other examples where we are trying to discover things we do not know. So you see here, for instance, a variety of dynamical systems. And what we are trying to do is discover them from data and compare to the benchmarks that are available, which are these two-step symbolic regression. And then I'm going to say a few words also about the opaque neural ODE. So what you see here is, for instance, in the paper we have many results, but here you see results for dynamical systems where we are trying to capture asymmetric growth with saturation. And you see, for instance, a Gompert model and a generalized logistic model being unraveled on the basis of data, and you see the probability of success. And what you see is that the code significantly outperforms the two-step symbolic regression. And this performance is even better when we increase the noise size, the noise or the step size of sampling. In that case, the success probabilities for our method are significantly better than the benchmarks. What about even a trickier scenario, for instance, a scenario where we have a chaotic system, a non-periodic system as well? What do? We see that in this case, decode again is a lot better than things like symbolic regression and two-step symbolic regression. But what is also interesting to see is that even opaque methods such as neural OD fail to capture the behavioral of the system. So as I mentioned, this is very encouraging. But ideally, what we would like to do is we would like to take these discovery methods to real data. And ideally, we would like to learn, for instance, from clinical trials, in this case, clinical trials of cancer patients. We have 8 clinical trials from which we are trying to learn. We are trying to learn whether we can discover dynamical systems under intervention. And what you see here is what, for a particular patient, what you see is this patient has been intervened on. And what you see is that initially, the tumor is actually decreasing. And after a certain period, the tumor volume increases again because we have relapse. So what you see again is what the code has learned. And we do not say that this is the right equation, but what we do say is that it is simpler than what symbolic regression was able to do. And it's also able to capture this trend which we see in the observable data. Okay, so this talks about a possibility of discovering equations. Many more equations, you can find them in our paper. But we are very excited about doing discovery in medicine, in particular physiology and pharmacology, and more generally in science. And pharmacology is especially an interesting area for us because we collaborate with pharmacologists in 3 different continents and numerous of them. And they are really the scientists, are important, prominent scientists in drug, in let's say, in drug discovery and drug administration and in clinical trials. So we really want to join forces with them to empower them to discover better pharmacological models. And what you see here is a summary of many of our collaborations and some of the work we have done. Now, often, unfortunately, these equations may be misspecified or incomplete. Also, they may be discovered based on variables in the lab, and they are difficult to bring to the clinic. What can we do in that case? What can we really do in the case in which these models that I'm describing are incomplete or incorrect? And how can we bridge the gap between pharmacology to what the patient is given in the clinic? And this gap is going to be really matched and overcome by learning. And this problem is ubiquitous, appears in healthcare, but appears in other areas. I used to do a lot of work in economics in the past, and there we build a lot of microeconomics or macroeconomics models, which need to be brought to the real world. And often our models are powerful and you can analyze them. But when you think about the messy, complex, high-dimensional real world, you need to create this bridge. So what I'm describing here is for healthcare, but this is... And this problem is not an imagined one. It was one that was given to us in COVID-19. Our lab did a lot of work in COVID-19 with medical institutions throughout the world. And one of these challenges that we got related actually to administration of drugs with dexamethasone, which was the first approved drug for COVID-19 treatment in the UK, but also in the Netherlands. And this is a drug that's very well understood, but for other indications. And the trouble is that repurposing it for COVID-19 patients was tricky. And the challenge is how to do personalized dosage, precision dosage. How much dose you should give to a particular patient, what medication you should be giving, and what level. And the reason this is challenging is we do not observe in COVID-19 patients the immune system activation. Yet it is very important to know that and infer it from data to be able to know how to dose the medication. And if you are giving a too high dose, it's a problem for autoimmune problem. On the other hand, too low may lead to a slow recovery, secondary infections, and depending on the patient characteristics, you need to know how much dose to give. Now, what happens is in the lab, pharmacologists have very precise pharmacological models. So the PK/PD model for dexamethasone is well studied, and it's actually an ordinary differential equation of the type I described to you before. This was not discovered by Decode. This was discovered by clinical pharmacologists who developed a compartmental model, a PK/PD model, that is really measuring the dynamics of the autoimmune system, and it helps understand how much dose you should be giving. However, the challenge is that this PK/PD model, this dynamical model, system model, involves information, expert variables, which are measured in the lab, but not in the clinic. In the clinic, you have things like a C-reactive protein, which you measure, but internally in the lab, you are measuring parameters that are measuring markers of the immune response, and that is routinely measured in the laboratory setting, but not in the clinic. So our goal was, can we take this type of equations, dynamical systems, this case, again, discovered by humans, maybe in the future discovered by Decode, and bring them to the bedside in the era of COVID. So what we did is in this paper that was very much the brainchild of Zhaoji, my former student, my current postdoc, we created what we call a latent hybridization model. And what this latent hybridization model does is we take this expert model, which is the ODE, and we embed it within a system of neural ODEs in order to really deal with the incompleteness and misspecification associated with this expert model. So in this way, we embed this expert model, which is a collection of expert variables that we do not observe, and the ODE that describes the evolution of these variables into a larger latent variable machine learning model, which is in this case a system ODE. On the basis of this, we will be able to make both predictions with very few samples, as well as be able to provide the transparency needed for clinicians to determine interventions. So, as I mentioned, PKPD models are well understood, and they measure these variables that are not observed in the clinic. But in the clinic, we observe other measurements, other biomarkers and endpoints, for instance, the C-reactive protein. Now, what we do with this latent hybridization model, we are able to infer on the basis of the data we have. You see here, for instance, 2 patients, and you see the C-reactive protein, which we measure in the patient. On the basis of this, we infer these variables, which are the expert variables, the immune response and the dexamethasone concentration. We do not have access to in the clinic, but we can infer them using this latent hybridization model. Then we are able to enroll the PKPD model, this expert ODE model, and be able to tell and assist the clinicians in an interpretable way, because the ODE is interpretable, and these PKPD models are routinely used by clinicians to determine how to give treatment and interventions to different types of patients at different levels. What's exciting about this is that this was not only a NeoRIPS paper, this became a real used idea. And you can read in our paper pages and pages written by the clinicians who have used this system. And what's also very interesting is that that was not only very transparent and actionable, but we were also able to learn quite effectively with just 100, 200 patients, which was very important. And it's an area where machine learning usually cannot achieve good performance. We need hundreds, thousands of patients to be able to achieve the same level of performance. Now, I talked quite some about ODEs, but what about PDEs? For a long time, I thought that this will really be, let's say, a bar we cannot overcome. And the reason behind that, this is notoriously difficult to search in. We know that the variational trick which we use in the code may not work. But again, I'm fortunate to have mathematician turned machine learner, Christophe, which together with Zhao Ji were able to conquer this problem. And we are able now to, for the first time, discover closed form PDEs from data. This paper appeared last year at NeoRIPS, and kind of what it does, I'm going to just describe in a nutshell, but Christophe is here so you can discuss more with him. In a nutshell, it relaxes a lot of the assumptions that current methods make. And for instance, the evolution assumptions or linearity combination, the equations need to be in the linear combination form. And often the existing methods were only working on explicit first order ODEs. And what we were able to do, were able to relax these assumptions and be able to show that for any PDE that has can be expressed in the following form, has a derivative bound and a derivative free bound, we are able to solve the problem. And the reason behind this is that any PDE that can be expressed in this form, the terms containing the derivatives, which are this so-called derivative bound part, is the one that's tricky. On the other hand, the derivative free part can be evaluated directly from data and can be as complex as you like. So this is the easy part, and this can be as complex as one wants. We do not need constraints here. What we do need constraints for is the derivative bound part, and this does require some technical constraints for the variational trick to work, but they are a lot easier than the ones that are currently made in the literature, and it allows for a much broader class of PDEs to be discovered. And we use this novel characterization of PDEs to define what we call variational-ready PDEs, which are currently the broadest family of PDEs that admit this variational formulation. So with this, we are able to develop also an algorithm which doesn't make assumptions about the conventional evolution assumption or the linear combination assumption, but rather, as I mentioned, provides a very elegant algorithm which uses the variational formulation on this class of variational ready PDEs and searches through the all-closed derivative-free parts and searches through a linear subspace of the derivative-bound parts. This cipher is an elegant algorithm that also involves some innovative optimization mechanism. So again, if you are interested, take a look not only for the power of it, but also for the elegance of it. The reason I'm especially excited about this is that if it is to discover governing equations, we want to move beyond just modeling tumor growth, pharmacological models under interventions, epidemiological models, but also spatiotemporal models. And these are important in general, whether it is modeling things like cancer or population models more generally in medicine, population health, and epidemiology. Now, you will say, well, it seems to be a gap here. You are talking about the discovery of these governing equations, but you need to make a link to causality. What is the link between the two? And since our lab is working both on discovery as well as causality, it was natural for us to seek such a link and see how the two relate. And we know that often what we are interested, if it is to bring causality in the longitudinal setting to estimate treatment effects for data, we want to understand when to intervene, how to intervene, for how long to intervene. And often what we would like to achieve is to have some form of ODE discovery and ODE as causal discovery. The two fields are somewhat separate, and they possess some advantages and some disadvantages, and hence a bridge needed to be made between the two of them. So first, why would we want such structural equations, and why we believe they are, if you like, higher on the rank of this ladder? First, they are interpretable. They work for irregularly sampled data and continuous trajectory in a natural way. They have a smaller hypothesis space, and they lead to better performance in quite a lot of scenarios. On the negative, though, if you take things like the discovery methods that I described to you, they use data in different ways, and they address slightly different problems. And often static features are not considered in ODE discovery, where only a single equation is found for the entire data. So diverse type of treatments are often also used. And also in our lab, we looked at continuous treatments, binary treatments, categorical, multiple treatments, which is something that such ODE discovery method will need to handle if it is for this bridge. Again, I'm very fortunate to have brilliant students that are also keen to talk to each other across the different expertises in the lab. And this is when Christophe, who is a mathematician, talked to Sam, who is an engineer, talked to Jeroen, who is a computer scientist, who knows a lot about causality, as well as Zhaoji. They joined forces to create this bridge. So in a paper that will appear next month at iClear, we provide a general framework which connects ODE discovery with treatment effects. And what is our contribution in this paper is the first usable framework that allows us to translate any ODE discovery into a treatment effect formulation. And while other treatment effect inference methods have used ideas from ODE discovery, inclusively in our own work, as you are going to see a little later, none has focused on ODE discovery, and this is really the culmination of all this. And in this paper, we are explaining the differences between these ODE discoveries and the treatment effect literature, and build a framework to really a method that uses this framework as well, which we call InSight. So usually when we have a longitudinal treatment effect data set, we know that it has biased samples. This is what you see on the left side. And if you look at the treatment effect literature, often will create some form of representation of the data. I will talk more about what usually we do in machine learning later, but we usually create some form of powerful representation from data, and then we will use this representation for inference. On the other hand, what we do in our method, we learn an ODE, but this time we no longer learn an ODE that's for the entire population, but rather an ODE which is refined for each specific patient in the data set. So this is actually very exciting, plus interpretable. To do that, we needed to reconcile in our paper quite a lot of discrepancies between assumptions, discrepancies between the fact that we have treatment plans that may be discrete, and we have variability across subjects. So it is these three assumptions that really need reconciliation, and we are able to do these reconciliations in 3 steps. First, we transform an ODE discovery method into a treatment effect method, resulting in a new set of identification assumptions. And this does not need to be a limitation, but quite the opposite, can be seen as an extension of the typical treatment effect identification assumptions, which may not hold in the ODE discovery settings. So we accept the ODE discovery assumptions. Number 2, we incorporate treatment plans as dynamical systems. And we are dealing with the interventions in that way. And then finally, in a classical ODE discovery setting, we usually have only one kind of between subject variability corresponding to the noisy measurement. However, there are a few other sources of variability that we need to account for if it is to use the ODE discovery for estimating treatment effects from data, and we needed to create this bridge to do so. Again, I'm sure that Jeroen and Christophe would be delighted to tell you more about that. I'd like here to pause and say that what I talked about so far, I hope I excite you about this new frontier that I call the discovery frontier in causality. And the reason I think this is interesting is that if it is to make discovery in the real world, we shouldn't just do discoveries for drugs. We also need to do discoveries in science, discoveries of the human system and a dynamical system, whether it's physiology, whether it's pharmacology, and beyond. And hence what we have is, we have on one hand data and machine learners that inform scientists. You see here a scientist who is enabled in their discovery to discover structural knowledge, and they will need to take and validate this information rigorously. But after they have done so, this can inform the machine learners, which can then hybridize these discoveries with other type of data that may not be observed in the lab, much more high-dimensional data, thereby creating hybridization algorithms such as the latent hybridization model, which can then be used to empower people that are needing to act in the real world, in our case, the clinicians. Okay, now let me go back in time. That doesn't mean that the world of causal effect inference doesn't play a role. As I mentioned, we are very excited about discovery, and we still feel that this is kind of the next frontier. But over the past almost 10 years, we have worked to build machine learning for causal effect inference, first in the static setting and more recently in the dynamic setting. Most of our work, even though we are machine learners, and even though I was a colleague of Judea Pearl, comes more from the Neymar Rubin perspective. And this is the area where that we fell in love with. We felt it was very powerful and built a lot of work. And you may wonder, what does a machine learning group have to add here? Very early on, we discovered that as machine learners, we are able to have very flexible end-to-end differential model architecture that enable us to really model the treatment assignment variable in a sophisticated way, thereby creating sophisticated architectures that deal with complex causal effect inference problems, as well as with the ability to deal with selection bias by, for instance, crafting loss functions to train powerful architectures. over almost a decade, we have done here just a few works, but maybe the lab has produced very, very many other works. We started with binary treatments. We started to look at multitask Gaussian processes and deep kernel learning with another former members of our lab, Yao and Alexis. Yao is in Stanford right now working with Emmanuel Handez, and Alexis is at Google DeepMind. But also other areas. We looked at not binary treatments, but multiple treatments, because often in cancer and many other settings, we need to look at multiple treatments and use GANs. We started to look at continuous dosage, and for that we repurposed and created some new forms of GANs with Ivana Bika, again a former student working on causality in our lab now at DeepMind. And even more recently, with a student that's just finishing, a brilliant student, Alicia Kurt, we developed meta-learners. Just some of the works that come from our lab, but see more, I invite you to take a look at our website and see more of the work that we have done using machine learning to estimate effects of inference in the static setting. How can we make real-world impact, though? In a paper that's embargoed, and only on Friday you are going to be able to see it online, we have walked all the way to trying to really understand what is still needed to make real-world impact in the hospitals and clinics. So together with collaborators from several institutions, most prominently Stefan from LMU, we developed this quite comprehensive paper where we look at causal machine learning status in the medical world. I mentioned to you, and have been pioneering in that area because we feel that the science of medicine starts with physiology and pharmacology. So a lot of early work used these ideas in causality that we developed in our lab and try to bridge really this bridge between machine learners like us and the scientists of medicine, the pharmacologists. And here are two papers done with collaborators over a span of almost 3 years, highlighting the advances of treatment effect inference in pharmacology. But as I mentioned, if it is to do true impact, we need to go beyond static data, because the reality is we have patients that are changing over time and they need to respond to treatment over time. We need to understand when to treat, how to treat, and when to stop treatment. And this is, of course, a tricky causal inference problem, and I do not need to this group to highlight the challenges associated with it. I'm going to highlight, though, the excitement, especially in the area of medicine. And clearly, we have the opportunity to learn from electronic health record data, such causal inference models, with a hope to provide recommendation systems to clinicians for the patients in front of them. To do so, we need to deal with the elephant in the room, which is time-dependent confounding, which of course occurs when patient covariates are affected by past treatment decisions, which in turn influence future treatment decisions and outcomes. We all know important early work from Robin, Hernan, and Brumbach. And initially, what we wanted to do is we wanted to kind of take these brilliant ideas from epidemiology and bring them to the world of machine learning through recurrent marginal structural models. So our first step was really reusing the architecture and the way of thinking and just replacing linear models with machine learning models. But very easily, we discovered that when we are taking them with complex data sets, such methods are quite numerically unstable and lead to high variance. And this is what it obliged us to think about a new way to do representation learning for causal effect inference over time. And this is some of the earlier work we have done, which is called counterfactual recurrent network, where we are learning sequence-to-sequence architectures to learn how to intervene and how to intervene over time, and address this issue of treatment invariant representations, creating treatment invariant representation through domain adversarial training. So using, rather than propensity scoring, inverse propensity scoring, this domain adversarial training as a solution to this idea. This performed a lot better, but we are still quite far from where we wanted to be. And part of the reason is that often in these models, the assumption was that the observations are fixed, but the reality is that these observations in electronic health records are not fixed, they are irregular. So we need to learn in the presence of irregular sampling. And the way we were able to provide a first solution to this is by providing a solution based on neurally controlled differential equations. And in this way, we are able to estimate the treatment effect using these neurally controlled differential equations. And the key idea was to learn a continuous latent representation of the patient states as the solution of this controlled differential equation. And first, we encode the representation up to a particular time t and learn a continuous latent path z as the solution to the CDE. And then for a future treatment plan, we decode future treatments and update the latent state via a second CDE. And finally, we deal with counterfactuals and we deal with time-dependent confounders via domain adversarial training, like in Schaar. Again, not the end of the story, because the data is irregular, but it is also informative. The fact that the patients come to the doctor or not is important. And we need to learn under informative sampling. And this is actually something we have started to make a little progress on. We feel that the problem is very challenging. I hope some of you will be able to help us with this. And the reason this is challenging also is that this would lead to potentially additional sources of bias that we need to deal with. We made some initial first progress in a paper that appeared last year, but again, we need other ideas and better ideas to deal with this. We just use intensity importance weights to kind of counter this issue, but we believe more is possible. Now, let me in the last moments of this talk about causal deep learning. And why is this so important? We all know in this group causality, and we all believe that it can have a great potential. But the reality is it has only limited real-world impact. And the reason is we have strong assumptions. Often these assumptions are untestable. They neglect many of the causality works that appear, especially in the computer science domain, focus on structure, but not the functional forms that are associated with the variables interacting with each other. Also, time is often neglected. And all of that makes it the work not to be very useful in practice. And as in our lab, we are very focused on not only doing beautiful theory or beautiful machine learning, but trying to have a real world impact. As a matter of fact, I wrote quite a lot about that in the last 1 year. So if you are interested to read more about what I think AI needs to do to make a real world impact, I invite you to take a look on our website on the reality-centric manifesto. And just today, our PLOS digital health paper appeared, where we talk a lot about machine learning for healthcare that matters, and changing the current world that either focuses on technical novelty or just beautiful theory into a world where we want to make real impact. And it is really under the vision of Jeroen that this work of causal deep learning, and Jeroen is here with us as well, so I hope he'll be able to talk to you, that we developed this causal deep learning manifesto. And what we want to do here is to move from the ladder to what we call a causal deep learning map, in a goal of trying to really bring the world of causality closer to practitioners. And we would like to do that in 3 steps. First, we believe that right now we have almost an all or nothing game. We have either the world of association or the world of causality, but we would like to have something that we call the rank 1.5, which are plausible causal structure, partial causal structures, which could still be useful to develop these methods in the real world. And for that, we are focusing in causal deep learning on real-world problems by identifying very clearly what are testable assumptions, what are not testable assumptions, and making that very clear to the practitioners. And again, there are a large number of plausible structures that we know and love in the world of machine learning and statistics that can inform causal deep learning and make an impact. And again, on this ladder, we are talking about the structural ladder and these different points on this ladder that we think are very important. The reason this is not just a ladder, but it's a map, is because we think structural equations are key. The conventional known ladder of Judea does not allow us to differentiate between at the extreme non-parametric models or highly parametric models. And this is very important, again, if you want to make real-world impact, because you may want to differentiate between machine learning models and, for instance, linear models. And again, what we would like to do is we would like to have stricter and stricter assumptions that are identified and provided by methods, such that we understand how the different methodologies that are provided are going on the structure, on the functional scale in terms of these assumptions, and whether the practitioners are willing to make these assumptions for their real-world applications. And again, we have in our paper this, let's say, these different these different points on this axis characterized. Finally, we feel that time is very important, and this is why the very beginning of my talk started actually with this idea of causality over time, discovery over time. This is why in our lab we spend so much time on it, because we feel causality is really a temporal phenomena, and hence this other type of axis is very important. So what we would like to do is we would like to embrace again Judea's vision and try to really use this vision to bring it to the real world in the form of causal deep learning. And we hope that with it, real-world impact can be made. In view of time, I would like to stop here. And I want to maybe just tell one more thing. I talked a lot about Christophe and his work. And actually tomorrow we have at 4 p.m. UK time, something that we call Inspiration Exchange, which is an engagement session that we have open to everyone that wants to participate. And Christophe is going to talk about some very exciting new research that he has been doing on AI for science, and he's very much on this discovery ladder. So if you have time, please drop by online tomorrow at 4 p.m. You'll have more opportunity to discuss with Christophe and learn some new things that I didn't present today in that talk.
Great, thank you so much for the very nice talk. Yeah, maybe we now switch to the second part. So as we said before, this is now a little bit more experimental. So yeah, to any of the attendees, if you have questions, just raise your hand and we will kind of promote you to be a panelist, and then we can have an open discussion between everyone. We will also stop recording so we can